Nervous?
Yes.
First time?
No, I've been nervous lots of times.
Quadratic equations. Over the course of the year, we've gone over 4 different ways of solving quadratic equations. You can see on this page the overview of each of them. I'll go through an example of each so you can see how you would use each one. The first one's taking square roots of both sides. That's whenever you have a perfect square variable that you can easily isolate. If you look at the first two, what I mean by perfect square variable is that I have exactly one x, it's a square, whereas here I have 2 different values of x and they're not both squares. So I'm able to isolate this perfect square, which is 25 x squared equals 75. So I've isolated that perfect square. In fact, if you want to divide both sides by 25, you can. 75 divided by 25 is 3. And since I've isolated x as a perfect square, I can go ahead and take square roots of both sides to get rid of that square. And recall that whenever you take square roots, you get both a positive and a negative solution. So I end up with, as my final answer, x is plus or minus the square root of 3. So it's the fastest method for solving for the value for x in that case. When factoring, you'd factor this expression as we would any other rational expression. I need, in this case, to find this particular summing product. The sum is -1, and since my coefficient is 2 of my a term, my product is going to be -2, which is 2 times -1. The numbers that will add to -1 and multiply to -2 are -2 and +1. So I'm going to split my middle term into those two, or you could also think of it as doing it with the 3-bridge method. So my first bridge is 2x squared. My inner and outer bridges are 1x and -2x. So these coefficients for these middle two, recall, come from this process. Then I'm looking for GCFs for my first and outer, which is 2x for both of these, and then each edge is a factor that makes up that product. So if this is 2x, this would have to be x in order to get the product of 2x squared. This is 1x, this will have to be +1. This is -2, this will have to be -1. And this isn't just an expression, it's an equation, so all of this is equal to 0. And recall that when I have a product of 2 factors equal to 0, by the zero product property, one of those 2 factors has to be 0. So what I'm going to do is kind of clean up the space so I can continue to solve this. So once I have it factored, I'm just going to clean this up. Okay, so now I have either 2x plus 1 equals 0, which would mean that x is -1/2 when I subtract 1 and then divide by 2, or if I have this one, x would be 1. So my solution set is either -1/2 or 1 for my 2 values for x. Okay, scrolling down. Completing the square. So this is when I cannot factor. So if I look to factor this one, I'm looking for something that has, since the coefficient is 1, a product of 1 and a sum of -6. There's no 2 numbers that do that for me. And if my coefficient is 1, that's when I will use completing the square. If I have another unfactorable one like this one in quadratic formula, if the coefficient's not 1, that's when I'd use quadratic formula. So that's how you would tell the difference between the 2 methods. The methods themselves, for completing the square, I'm going to isolate all my variables to one side. So this will be equal to -1. Then I'm going to make this into a perfect square so I could solve by taking square roots like I did in the first example. So I have to take half of this middle term as -3 and then square that. So I'm going to add 9 to this side. But don't forget, in order for this equation to be equal, I don't just add it to the one side, I'm adding this 9 to both sides. I end up with this left-hand side will now factor to x minus 3 squared, and my right-hand side, -1 plus 9, is 8. So I'm going to continue this by taking square roots, and when I take square roots, there's a plus or minus. So I'm going to move up here. Square root of a square, those are inverse operations, so they do undo each other, and then I'll have plus or minus the square root of 8. The square root of 8 has a perfect square factor of 4, so this is really plus or minus 2 rad 2. Then I'll solve for x by adding 3 to both sides, and I have 3 plus or minus 2 rad 2. Final answer. In the quadratic formula case, again, you can identify that by first checking to see if it factors. 3 times 7 is 21, so I'm looking for things that multiply to 3 times 7, which is -21, and -1. There's no 2 things that add to -1 and multiply to -21, so this is not going to factor, so that method I'm going to abandon. Since my coefficient of the x squared term, the a value, is not equal to 1, I can't do this by completing the square, so I'm left with quadratic formula. Now for any quadratic written in standard form, that's the formula for the final answer. So in this case, my a, which is the coefficient of x squared, is 3, my b is -1, and my c is -7. So I'm going to plug all those values in and reduce. Negative b would be 1 plus or minus the square root of b squared, which is 1, minus 4 times a, which is 3, times c, which is -7. All divided by 2 times a, which is 3. Okay, so I'm going to rewrite this slightly simplified. This is 1 plus or minus the square root of, well, 4 and 7 give me 28. 28 times 3 gives me 84. So this is 1, and since I have 2 negatives, it's plus, so this will be 85 over 6. Then I'm going to see if there's any perfect square factors inside of 85. 5 is clearly a factor, so let's factor 85 off to the side so we can see what its perfect square factors are. 5 is a factor. It goes into 8 one time and into 35 7 times. So it's 5 and 17, which are both prime, which means that 85 is not going to reduce, which means that this is my final answer. Okay, so let's see how we could select our appropriate method based on that little bit of review. Well, first let's get this in standard form so I can see what's going on. So this is x squared minus 10x minus 35 equals 0. Since I can't quickly isolate a perfect square, I'm going to see if this factors. So two numbers which multiply to -35 and add to 10. So I need a product of -35 and a sum of -10. Well, 35's only factors are 7 and 5. Okay, but those don't add to -10, so it doesn't look like this thing is going to factor. So now, if it doesn't factor, I'm going to check my leading coefficient, which is 1. So the fastest way to solve this will be by completing the square. So let's get all my variables to one side. X squared minus 10x is equal to 35. I left some space for that completing the square process. Half of -10 is -5, and -5 squared is 25. So I'm going to add 25 to both sides. Okay, my left-hand side now factors to x minus 5. My right-hand side, 25 plus 35, gives me 60. Okay, so I'm going to solve by taking square roots now to get to my x, because this square is standing in the way. So I'm going to square root this, square root this. Remember, there's a plus or minus whenever you take square roots. So this is x minus 5 is plus or minus the square root of 60. Now 60 is 4 times 15, and 4 is a perfect square. So this is really plus or minus 2 square root of 15. So that means that x is 5 plus or minus 2 rad 15. Okay, moving on to the second one. I have a coefficient of 2, so I'm going to see if I can factor this again. Sum and product. There's no perfect square to isolate, so I need a sum of, or I need a product rather of -14 and a sum of -8. Well, the only two factors in -14 are 2 and 7, or 14 and 1, neither of which add to 8, so again, this won't factor. But now since my coefficient is not 1, I'll have to do this by quadratic formula, so that'll be 8 plus or minus the square root of, and if it helps, you can do this b squared minus 4ac stuff off to the side so that you write your simplified answer in here. That'll be 64 minus 4 times 2 times -7. Well, 4 times 7 is 28, and 28 times 2 is 56. So this is 64 plus 56, which gives me, let's see, 70, 130. Wait, 70, so 120, sorry, 120. Well, so this is the square root of 120 all over 2 times a. The a value is 2, so this is over 4. So let's see if this reduces. I have 8 plus or minus, now 120 is 4 times 30. Now in 30 is 15 and 2, but those aren't any perfect square factors, but I could take out that common factor of 4, so this will be 2 rad 30 over 4, which means that x is, there's a common factor of 2 between everything, so this will be 4 plus or minus the square root of 30 all over 2. Okay, now there are 2 more examples for this on the next page. I'd like you to try these 2 examples on your own.
Surely you can't be serious.
I am serious. And don't call me Shirley.
Keep in mind you have to first get them in standard form, so you have to distribute these values, this A, to both of these terms, and then get this in standard form. You also have to get this in standard form, and then determine which method you want to use. For now, we're going to look at the discriminant. The discriminant is a way for telling us the number and nature of the solutions of a particular quadratic equation. It also tells us if it has any x-intercepts or not. So, which you could recall, we actually did this part when we did parabolas. But here are the 4 cases for the discriminant. It could be a positive number and a perfect square, like the number 81, which is 9 squared. It could be a positive number and not a perfect square, like the number 11. It could be exactly equal to 0, or if it's negative. Now, it turns out when it's negative, we don't really care whether or not it's a perfect square. So here's what happens in each of these situations. Whenever it's positive, you're going to have 2 roots. So regardless whether or not it's a perfect square, if it's ever a positive number, you have 2 roots. If it's 0, you'll have 1 root, and if it's negative, you have no roots. So since it has no roots, it doesn't make any sense to talk about the nature in that case, so we'll ignore that column. If it's a perfect square, however, it will have rational roots, meaning it's a number like 2, 5/3. It's a number that can be represented as a fraction. If it's not a perfect square, you're going to have irrational roots, which is like radicals, or the number pi is an irrational number. If it's equal to 0, it also turns out to be rational. So whenever it's a perfect square, you have rational roots. If it's not, you have irrational roots. Now, number of x-intercepts. Well, the roots is just another way of saying x-intercepts. So the x-intercepts is exactly equal to the number of roots you have. So I have here, and then here I would have no roots, or no x-intercepts. So if I'm using those values in an example, find the number of nature of roots of each of these examples, the first thing I'm going to do is get it in standard form. So this will be 2x squared minus x minus 10 equals 0. My a, b, and c value come from this equation, and I'm looking for the discriminant, which is equal to b squared minus 4ac. So in this case, my discriminant, which is b squared, so that would be negative 1 squared, which is 1, minus 4 times a times c. When I multiply all these values together, negative 4 times negative 10 is positive 40, times 2 is 80, plus 1 will give me 81, which is a perfect square, so I have 2 rational roots. So that's the number is 2, the nature is whether or not it's rational or irrational. Now you could also use this exact same value to determine the x-intercepts of this equation. So since I have, it's already in standard form here, I know my a, b, and c values, so I'm going to calculate my discriminant, which again is b squared minus 4ac. So this will be 36, since b is 6, c is 10, a is 1. So b squared is 36 minus 4 times a, which is 1, times c, which is 10. So this becomes 36 minus 40, which is negative 4. Since that's less than 0, I will have no roots. So there's no solution or no roots. No roots. Or no x-intercept is what I should say. Finally, fractional equations. Now there's 2 methods we can use for fractional equations. When you have a fraction, much like this case, where it's exactly one fraction equals another fraction, the quickest method for solving is basically just cross-multiplying. When I cross-multiply here, I end up with 3k squared minus k equals k plus 3 times k plus 3. Now, a common mistake is people write that as k squared plus 9. That is 100% wrong. These are 2 binomials, so you will have to distribute them out. And when you distribute them out, you end up with k squared plus 6k plus 9. So it's basically foiling. I'm going to put this in standard form. I end up with 2k squared minus 7k minus 9 equals 0. I'm going to try to factor that, so I'm looking for a sum and a product here. The product will be 2 times negative 9, which is negative 18, and the sum is negative 7. 2 numbers that do that for me are negative 9 and positive 2. So I'm going to do this time by the AC method. So I'm going to split my middle term into minus 2k plus, sorry, I have that backwards. Split that into minus 9k plus 2k. Again, those coefficients come from these two numbers. I'm going to bring down my other terms, so that's 2k squared and minus 9 equals 0. Factor by grouping. So for my first group, I have a common factor of k. I'm left with 2k minus 9. For my second group, I have a common factor of 1, so I pull out a 1 times 2k minus 9 equals 0. I now have a common factor of 2k minus 9 from each of these terms. So that's 2k minus 9 times k plus 1 equals 0, which means that either k is equal to 9 halves or k is equal to negative 1. So those are my two solutions. Now, the last thing to check whenever you're solving fractional equations, you must always check that none of your denominators, no denominator is equal to 0 for the solution you got. So if I plug in negative 1 here, neither of my denominators are 0. If I plug in 9 halves, also neither of my denominators are equal to 0. So that's a quick and easy way for solving when you have two fractions. But when you have more than one, we had another method. And it was basically multiplying the entire equation by the LCD. So the LCD in this case, if I factor this term, is m plus 3 times m minus 3. And my LCD needs to represent each of those factors, so I need a factor of m plus 3 in my LCD. Then I need to multiply on a factor of m minus 3. Then I already have, for my last one, my m plus 3, and I already have my m minus 3. So that's my LCD. I'm going to multiply this entire equation by this. So this entire equation is being multiplied by the value of that LCD. So it's getting distributed to every single term. Now what's convenient about this process is that since this LCD represents all the factors of every denominator, all these denominators are going to cancel out. So when I look at my first one, I have this first whole term, 6m over m plus 3, times this. My m plus 3's will cancel out. It leaves me with 6m times the m minus 3 of the denominator. My second one, when I multiply it onto this denominator, my m minus 3's will cancel out. It'll leave me with the m plus 3 times this, so that'll be m minus 6 times m plus 3 will be equal to, and then what's very convenient is when I multiply this LCD times this term, all of these factors will cancel out, so I'm left with just m times 5, or 5m squared minus 12. I'm then going to distribute all my terms, so this gives me 6m squared minus 18m. When I FOIL this out, I get m squared minus 3m minus 18, all that times negative 1. That's negative m squared plus 3m minus 18 is equal to 5m squared minus 12. So let's combine all my like terms and get everything into standard form. Well, what's very convenient here is I get 5m squared minus 15m plus 18 on the left-hand side and 5m squared minus 12 on the right-hand side. So notice my 5m squareds will cancel out from both sides. And when I bring my 18 over, I end up with negative 15m equals negative 30. And when I divide both sides by negative 15, I get m equals 2. So again, don't forget, whenever you're fractional equations, you have to check that no denominator is equal to 0. The easiest way to check that is to plug it into the LCD, which represents all the denominators. So when I plug 2 into the LCD, I do not get 0, which means my solution is fine. So I want you to try this last one on your own. Remember to check the solution you get into the denominators to make sure it does not make any of them undefined.